Hi everyone. In this video, we'll be discussing atmospheric pressure and wind. The atmosphere is made up of gases that have mass. The atmosphere has weight because this mass is pulled toward Earth by gravity. Atmospheric pressure is the force exerted by the weight of those gas molecules on a unit of area on Earth's surface. The pressure, temperature, and density of a gas are all related. If one of these variables changes, it can cause changes in the other two variables. In a closed container, the relationship among pressure, temperature, and density is straightforward. However, the atmosphere is not a closed container. These variables cannot be held constant, so the cause and effect relationships are quite complex. Surface air pressure may be influenced by dynamic factors. In other words, air pressure may be influenced by the vertical movement of air, as well as convergence and divergence. As a generalization, descending air tends to be associated with relatively high pressure at the surface, whereas rising or ascending air tends to be associated with relatively low pressure at the surface. In the slide, we can see that in the upper atmosphere, gas molecules are far apart, so density is lower, and fewer molecules are overhead, so atmospheric pressure is also lower. In the lower atmosphere, the molecules are closer together, so density is higher, and more molecules exist above, so pressure is also higher. In this slide, we see an example of a weather map with isobars. Isobars are lines connecting points of equal atmospheric pressure. When they have been drawn on a weather map, we can determine the location of high pressure and low pressure centers. As with other types of isolines, the relative closeness of isobars indicates the horizontal rate of pressure change. We call this the pressure gradient. The pressure gradient can be thought of as representing a steepness of the pressure slope. This is a characteristic that has a direct influence on wind. Air tends to move from areas of high pressure towards areas of lower pressure. We say this movement is the pressure gradient. If the pressure gradient force were the only force acting on our atmosphere, air would flow perpendicular to the isobars. However, because Earth rotates, any object moving near Earth's surface is deflected by the Coriolis effect. In the first image, we see a hypothetical movement of air that includes only pressure. In the second image, we can see the upper atmosphere that includes the Coriolis effect. Regardless of the initial direction of motion, any freely moving object appears to deflect to the right of its direction of motion on the northern hemisphere and to the left in the southern hemisphere. The apparent deflection is strong at the poles and decreases progressively toward the equator, where the deflection is zero. In the upper atmosphere, the balance between the pressure gradient force and the Coriolis effect results in geostrophic winds blowing parallel to the isobars. In the last image, we see the lower atmosphere. Here, friction slows the wind, which results in less Coriolis effect deflection. Wind diverges clockwise out of a high and converges counterclockwise into a low in the northern hemisphere. Cyclones and anticyclones also occur vertically in the lower troposphere. We can visualize the anticyclonic pattern as upper air sinking down into the center of the high, then diverging near the ground. Opposite conditions prevail in a low pressure center, with the air converging horizontally into the cyclone and then rising. Descending air is associated with high pressure at the surface, and rising air is associated with low pressure at the surface. Around the world in equatorial latitudes, warm air rises, producing a region of relative low pressure at the surface. This air ascends to great heights, mostly in thunderstorm updrafts. By the time this air reaches the upper troposphere, it has cooled. The air then spreads north and south, moving poleward, eventually descending at latitudes of about 30 degrees north and 30 degrees south, where it forms bands of high pressure at the surface. One portion of the air diverging from these surface high pressure zones flows toward the poles, whereas another portion flows back toward the equator. At the equator, the northern and southern hemisphere components converge and the warm air rises again. These gigantic convection cells are called Hadley cells, named after a meteorologist who, in 1735, first conceived the idea of convection cell circulation. The warm air that rises from the tropics is known as the ITCZ, or the Intertropical Convergence Zone. This slide shows an idealized global circulation pattern on Earth. Rising air of the ITCZ in the Hadley cell convection is deflected aloft and forms westerly anti-trade winds, while surface winds diverge from the subtropical highs to form easterly trade winds and the westerlies. The upper atmospheric flow of the westerlies is shown by the blue arrows. Briefly, we can see that we've got low pressure along the ITCZ, and then we've got high pressure buildup around 30 degrees north and south. We know, based on the pressure gradient force, that air flows from high pressure to low pressure. And then we also know that because the planet is rotating, we have the Coriolis effect, which will deflect those winds to the winds right in the northern hemisphere and to the winds left in the southern hemisphere. Be aware that just because you see in the image the arrows look like they're going to your left, they're actually going to their right. So it's from the direction of the wind that we have that deflection. These patterns continue across the planet, giving us the trade winds, westerlies, and the easterlies. Okay, I'm going to stop the video here, and I'll see you in the next one.